So today, hopefully we're finishing up differences and segueing into panel data by the end, depending on how fast I can talk. So just periodic Tuesday morning class timeline business. Today you already turn off the, I guess it's the second part of the data analysis, which is the setup. Due 1 week from today is something totally different, which is a research proposal question and data. So this is your chance in the intervening week to think about what it is you might want to write a research proposal about, if you haven't already. One key difference is, again, between the data analysis and the research proposal. The data analysis is something that you're supposedly actually trying to implement or could conceivably implement during the course of the semester. The research proposal is something that you're not expected at all to implement. The idea is that you're proposing to do something somewhat bigger scale than a single paper, and the research proposal should feature some aspect of going after a causal question, the causal effects of some explanatory variable, some policy, something on some measurable outcome. Again, for the data analysis, hopefully as you've told me by today, you have a data set or have access to a data set. The research proposal doesn't require at all that you have the data. Ideally, it would be good to know that it existed, but as with all this stuff, you should be using both these assignments for your own edification and advancement.
For next week, do you want like just the question and the data set, or do you want more than that? Because it says a page, but I'm not sure if you want.
I mean, you don't have to fill the page. It's
like, do you want like no background or anything like that, or just more?
I want. If it's helpful for you to write that down, that's great. But what I really want is you to have thought at least enough about this to write something on a piece of paper that says, I have a research question somewhere. Some of you take the assignments very literally, which I can appreciate, being a pretty literal person myself. But if I say a page, I usually mean not more than a page, as much as you need to, take as much space as you need to answer it, and I'll read what I can and want to. And then finally, not finally because this is an ongoing process, but 4 weeks from today is the deadline for the last part of the data analysis, the last required part of the data analysis, which is the initial analysis plan. So that should be your effort at coming up with a recipe, an algorithm, a set of directions for a program or for yourself to actually implement the analysis. I don't expect state of code, but you might want to write parts of this at least in what some people call pseudocode, which is just kind of spelling things out. I don't expect that you'll have answered every question, and that you'll have thought through everything in each part. It is an initial analysis plan, but I do expect that you'll have made a genuine effort to give it a crack. It's the experience of going through the exercise of specifying an analysis plan. So you should have something like data source. Where are you getting this data from? Specifically what years, if they're URLs that the programmer needs to fetch the data from, or a note about providing it's already downloaded, it's being secured from here, blah, blah, blah. Sample selection, that usually means inclusion and exclusion criteria. Who's in the sample, who's out of the sample? What are the names of the variables, or sort of, to the extent you have that detail, actually referencing the documentation to be able to say the variable is called, age or age 20 or whatever it is. That's useful stuff to put into the exclusion and inclusion criteria. Variable construction. Some of you may be using data sets that are quite clean. Some of you maybe not, but you'll probably have to deal with issues like missing data or uncode, like age is coded as a continuous number of years and it's top coded at 99 or something, or and there are missing values. How do you want to transform a particular key variable? I don't expect, again, that you've done this for all variables. I would expect you to pay more attention to the things that are most important to the analysis. The outcome, the key explanatory variables. Control variables you can certainly want to specify, but you don't have to go into painful detail. And then the model specification. Again, this is not a class about all the various flavors of regression analysis. So some of you, someone was saying about Cox proportional hazards regression before class started. We haven't covered Cox proportional hazards regression, so it's not your. You may know what it is, and if you think it's appropriate to use something outside of class for this class, that's totally fine as long as I can understand it. But, you know, the workhorses that we've covered are linear regression and, to a lesser extent, logistic regression. If that's all you know, that's fine with me, and fit your thing into those frameworks. It probably think that's why it's called the initial analysis plan. For some of you, this is the last stop in this path before you go back to primary data. Good luck. For others of you, though, you may want to push forward and actually take this stuff that you wrote down, which I'll look at, but which is primarily for your own, like, okay, it's an intermediate step along the way to producing this. Oh, that's not good. Okay, so any questions about anything class assignment related, Lisa?
Yeah, I think I'm still confused about this 1 versus 2. If we're planning to
1 versus 2?
Sorry, what's due today versus in a week? If
Okay.
we're planning to analyze our data with a research question, then it's hard to think about how those 2 assignments are different.
So we're talking about the data analysis setup, just like
No, the research proposal versus the data analysis setup.
2 different topics.
So
They don't have to be 2 different topics,
Okay, I
but
guess
this is something you would submit to the NIH or to
Okay.
RWJ or to
Okay.
you know, the output here is ostensibly an actual grant proposal
Okay.
to a funder. Could be the University Research Foundation, could be the LDI you know, pilot project thing. But this is a on spec sort of, this is what I want to do. This is an analysis for which you have a data set that you're actually actively working on. You don't ostensibly need funding because you have data for this, you have the data in hand and your time is worth, marginal cost of your time is 0 and you're going to do it all yourself, so you don't need that. And the output for the data analysis is at least an analysis plan, but maybe an abstract and ideally a manuscript. So while you're, you know, this is not blue sky, but bigger picture kind of like, but you get a research proposal, you won't hear back about it for at least some number of months, depending on who the funder is, if not years, depending on how long it takes to go through the grant of the NIH, which doesn't have any money anyway, kind of proposal. So like, some of you have asked me about how different these 2 need to be. They can be somewhat in the same topic area. It doesn't make much sense to propose to do research that you're already doing, so I would like, there's a fine line there. And for the purpose of the class, the proposal ought to involve something related to a causal question, whereas the data analysis in hand, I don't expect you to be applying the methods that we're talking about or haven't even talked about yet to the data analysis. Most of you are doing, I think, basic descriptive, not basic descriptive, but mostly a descriptive kind of analysis for the data analysis. Although I have to say, of those that I've been able to read so far this morning, they're really interesting questions. I hope you guys are enjoying, or at least not hating the data analysis project, because you know, like you got some good questions, and I think that they're interesting stuff. So I'm, as far as I can tell, it seems like those of you who turned it in and I've read look very promising. Kind of could lead to a manuscript kind of thing. So that's not super. You know, I mean, like, you know, keep working at it, but it's very promising in my mind. Did I answer the question?
Yeah, I'm just gonna come bother you. I think I did it backwards. It doesn't matter really.
I don't think you did. I mean, you're planning on writing a paper involving analyzing a particular policy for which you already have data, or you're going to be getting data shortly.
Okay.
Kevin's already got funding for your thing.
Yeah.
So
yeah.
you don't need a research proposal. So think of something else.
Oh,
But you
okay.
still have to write one.
Yeah.
It's like your next idea. Like,
Okay, I'm ready. I'm ready
Cool.
for another one.
You don't have to do anything, right? I mean, that's part of one of the
No,
mantras of the
I'll
class. You don't have to do anything, but you don't have to do your A either, so. Well, you don't have to do it. We can talk about that later. There's that. All right, can I move on with the timeline, or we all stuck on the deliverables? Okay, fine, good. All right, let me know of course, as time goes on, if you have any questions about any of this stuff. Oh, as far as feedback goes on today's assignment, though, it's unlikely I'll be getting anything back to you in a written form before next week. Most of my like my initial if you turned it in before 9:30 this morning, I probably scanned it quickly and thought it was fine. If you have specific questions or you're worried about something in particular and you need to see me urgently, let me know. And if you, like, my usual feedback on the kind of thing is like, oh, it looks good, this is where there might be some problems, you know, or issues to be aware of kind of thing that I'm thinking of going forward. But I don't usually, I don't have time, and I don't, like, usually it's kind of premature to give you totally detailed feedback. But if you want to talk about it, I'm available to meet, and so we can do that. Okay? All right, so in 75 minutes or less, or maybe even less than that, the end of difference and differences. I want to show you some cool code using the margins, commandants data, which I think is cool. And hopefully, finally, we'll start panel data, because we're running out of time. All right, so since I made you read it, or asked you to read it anyway, I think it's worth talking about, and also because it's a really interesting and good paper. The Rachel Warner, David Ash, and Dan Polsky 2005 paper called The Unintended Consequences of Coronary Artery Bypass Graft Report Cards. This paper appeared in the journal Circulation, which cardiologists may correct me, but it's my understanding is the top journal in the field of cardiology. And these are all pen people, so I won't say anything too bad about this paper, but I don't have to because they can all beat me up. But, not David probably. But it's a really interesting paper, and it's totally applicable to this. It's a screen, difference and difference and differences. So let's go through why that is. So first, a little background on the institutional details are important to understanding the paper. For those of you who weren't aware, the state of New York has been producing report cards that are available to the public on individual surgeons' performance, that is risk-adjusted mortality rates for CABG surgery. They started in 1991. This came out of a quality improvement effort by the State Commissioner of Health. It was never intended to be public, but Newsday newspaper sued the state and basically got a court ruling saying they were able to publish the information on surgeon level performance. And once that occurred and the data were published, the state got behind it and just kind of pushed it out. And New York was a pioneer. The other pioneer in this field was the state of Pennsylvania, which started producing CABG report cards in 1992 or so, right after. And there's been a lot of back and forth about to what extent these report cards have actually improved performance, but Rachel and company were looking at this particular issue of how these report cards might have some unintended effects on racial disparities in access to CABG. So if you think about a report card, it's important kind of, as a researcher, to play through, well, okay, what effects would we expect a report card to have on surgeon behavior in the absence of any data? How could they respond? How could any particular surgeon respond? So one obvious response is to ignore this information. It's quite plausible that surgeons don't know that, I mean, maybe not in New York, but in other places that they, or maybe even in New York, that just because the state is collecting this data, they didn't know it was public, they didn't know what was going on, they didn't have time to think about it, it's not relevant to the clinical decision, so I'll therefore kind of just completely, I don't have time to deal with this, I'll completely ignore it. Completely plausible response. If they wanted to, because they were motivated so to actually improve their outcomes, to look better on their report cards, because maybe their grandparents were, particularly their grandmothers, were looking at these report cards and saying, why were you, significantly worse? Why are your patients dying significantly more frequently than the rest of the state average? I can't believe you're related to me. That could induce all sorts of guilt and shame. What could you do if you're a surgeon? Two basic opportunities to respond. One is some sort of work harder, do better, whatever it is clinically, but we can't observe in data, do something to actually try harder. Another response, though, is to game the system, is to say, okay, let me look at this algorithm that assigns calculates my risk-adjusted mortality. It's based particularly on the risk-adjusted part, so whatever they capture, okay, those, whatever's in the algorithm for calculating mortality, that's fine, I'll be rewarded for that. But there are other things that I, as a surgeon, might be able to observe about a patient to say, all right, you have, some X score is worse than, is bad, and it's not controlled for in the logistic regression analysis that they use to calculate risk-adjusted mortality. You look sicker than that. You look sicker than you should, so I'm not going to I'm not gonna operate on you. Versus someone else might say, you look, you know, on this unmeasured thing that only I as a surgeon see, you look healthier than average. You're probably going to live, conditional on all these other covariates. So I'm more likely to give you surgery at that point. Well, so it may be harder to induce CABG surgery, to induce demand for CABG surgery because of the flow to the cardiologist, right, in this particular case. But it's certainly easy for me to say as a surgeon, I'm not going to do this. But the surgeons, they only get paid if I get paid the most if I actually perform the procedure, and cardiac surgeons who do CABG at the time certainly did kind of specialized in it. So, you know, does this story make sense? Does it make sense that a surgeon might actually actively avoid patients who look sicker than expected? And in particular, and this is where it gets kind of interesting, one of the things that the report card did not control for was patient race. And patient race, there's some evidence to suggest that patient race is predictive of eventual mortality, perhaps because they're more going to delay treatment, and so they're sicker when they get in a way that's not captured in the risk-adjusted, the risk adjustment process. Now, so the research question was simply, let's look at this initial publication of report cards. So at the very beginning, these report cards are brand new. In New York, no other states had them at the time. Did the publication of these report cards have a differential effect on the likelihood of minorities getting CABG versus other non-minority patients? Okay. And I will tell you, well, I'll talk about back in a second, there was a lot of hoo-ha. Rachel got into it with a guy named Ed Hannon, who was the guy behind the methodology, and there's actually an exchange. Rachel wrote a couple papers about this. There was an exchange between blanking on his name, the former commissioner who takes a lot of the credit for doing the report card adjustment. The idea, they said, that surgeons would behave in such a way is preposterous. And even if it weren't, it doesn't matter because our risk adjustment scheme is so good, it's state of the art. We actually, and it is, the New York risk adjustment scheme is quite good. It collects a lot of clinical level details. This isn't just an administrative database thing. They collect stuff like ejection fraction, blah, 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 coronary anatomy, blah, 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 that they get from, you know, that actually somebody, I think it's a nurse in the OR, actually fills out the patient case report and says, have this, don't have that. Nevertheless, it's impossible for them to collect all the information, as Rachel's point, and so there's still margin for the potential that surgeons are actually acting in this way. Preposterous, says the state of New York. We can't possibly believe it. So what do they use to actually analyze these data? Well, the report card came out in December of '91, so they need data before and after. So they used my good friend hospital discharge data from the state of New York, and they also got a set of 13 arbitrary selected control states for the 8-year period from 88 to 95. And these, as I've said before, these hospital discharge data are pretty good about information on patient risk factors, at least coded with ICD-9 diagnosis codes. But you know, there's still things that are lacking in the hospital discharge data, and that's another area where the state of New York people push back. How can you look at the discharge data? It's not as detailed. Well, sometimes you got to go to battle with the army you have, not the army you want. Also, let's just step back a second and say these data are a pooled cross-section. They're not a panel data per se, even though we're following the same hospitals over time in the same states over time. We're not following the same patients over time. It's possible that a patient could have multiple CABGs in a way that was one before and one after, or be eligible for kind of have heart disease in a way that would require CABG, might require CABG surgery. But we're not, the discharge data are at the patient level. And so we're treated as a pooled cross-section, and we'll talk more about why that matters later on. So the inclusion criteria, they didn't look at all CABG recipients, although they could have, right? We could say, why not examine all CABG recipients and compare racial breakdown in that population? Why wouldn't they have done that? Why might that not be such a bad idea to look at CABG recipients? I mean, we're looking at disparities in CABG receipt, right? So, how would you calculate a rate of CABG receipt among CABG recipients? What is the rate of CABG receipt among CABG recipients? 100%, right? So how do you know? The point is, if you look just at CABG and say like, well, they're more likely to be white or more likely to be black, Compared to what? You don't know, you can't observe who
didn't get.
was eligible but didn't get cabbage for, in the particular case. So they used heart attack, which Rachel and David and Dan didn't come up with. It's been used, well, it's been used in clinical literature a lot, but it's been used even in the economics literature a fair amount now. Heart attack is every health economist who doesn't know too much about clinical medicine's dream condition for a number of reasons. One, they pretty much always show up in the data. So if you have hospital discharge data, all payer hospital discharge data, and someone has a heart attack, if they didn't die before they got to the hospital, they're probably going to the hospital. You pretty good, you can claim credibly that you have a complete sample of hospitalized, of heart attacks. And AMI is nice because there's no way that the actual implementation of the report cards affected whether or not people had MIs, right? So there's no reason to think that publication of the report card certainly didn't lead to the incidence of MIs. Now what it might have done is say, you could make some crazy story about how publication of report cards in New York led to a mass migration or comparably an exodus or in-migration of people who likely to get MIs, right? So, now that New York publishes report cards on surgeon quality, I'm going to move to New York, and I'm also at high risk of having an MI in the next year, right? Or given the way that MI, it would be worse if it was a chronic disease. You're like, okay, I have cancer, and I'm going to move to New York so I can find out who the best providers are. MI is not nice, but it's acute. So you're not worried about someone saying, okay, I have an MI, now I'm going to move to New York, so I can then see figure out who to treat, who to get treatment from. It's not credible. It may be physically possible in some cases, but it's just not a serious threat to the research design. And that's really useful. I mean, they're starting off this case where they have a subpopulation of people who are at risk for the treatment, and that population is exogenously defined. It's impervious to the policy. So the outcomes on hypotheses, the primary outcome was receipt of cabbage. The money is, were minority patients less likely to get relatively less likely to get cabbage after the report card publication compared with a comparable population of non-minority patients. But they also looked at cardiac cath and PCI among MI patients as well. Why? Because these are kind of similar, in a blue sense, similar treatments, but they're performed by different physicians, and specifically, there are a set of treatments whose use should not, I think maybe we could examine this, but certain should not have been affected by publication of report cards for cabbage. So cardiologists weren't graded, only cardiac surgeons in hospitals with cardiac surgeons. So this is in some sense, a placebo test, but it also might say if there is an effect of cabbage report cards on racial disparities in the use of these things, you have to go with a story why that is. Is there something about collusion between cabbage surgeons and interventional cardiologists? Is there something that goes on here that might explain why these things might matter? It is possible. I think their story is consistent with the findings are consistent with a separation between these two market segments. So it's not necessarily a pure placebo test, but it's still something where we expect just up front, here's where we expect the policy to have an effect if our story is right, here's where we wouldn't. If this is a story about cabbage surgeons differentially avoiding patients based on their race, is it having spillover effects into the cardiology practice? They did this thing with, so one of the problems with the hospital, with the discharge data, was that race was missing more frequently than they would like. So it wasn't missing so much that the data weren't useful, but it wasn't missing so little that they didn't have to do something about it. They went through this whole imputation exercise using logistic regression. I have some notes on it. It's really kind of tangential to the story about what they did, because their response was to impute race and try it, and then use just the cases that had reported race on them and try it again, and the results were consistent. Not a problem, all right? Moving along, missing race isn't a problem. I suspect this was a referee comment, but maybe they came up with it on their own at that time. What do they control for? Well, they have information from the discharge data on demographics, so age, sex. They linked on zip code, median income. For those of you who are using data involving zip code, just know one of my personal pet peeves is that zip code is actually an acronym. It's properly capitalized. The ZIP stands for Zone Improvement Plan. Code is also should be capitalized, so go ahead and do that. Okay, we had this conversation. They also control for payer type, which you think also was, was legitimately matter. All these things are either kind of risk or might potentially influence surgeon's decision to operate on a patient. You want to have, as our counterfactual, minority patients and non-minority patients who are as close as possible, otherwise identical, except for their race. And they also control for the percentage of Black and Hispanic patients with MI admitted to each hospital. As a side, I think as a kind of a, let me finish the thought and then not a neighborhood level effect, but a context effect of kind of hospital, the effect may be different across hospitals that see different proportions of minority MIs.
So, was this in a time when hospitals were fighting to do so many cabbages so they could keep doing cabbages? Like, were there a minimum number that they had to do a year?
The volume standards had not come out yet generally, but cabbage was still a very lucrative thing, and it was at least if not on the upswing, it was a cash cow. I think it still is a cash cow. There's just a lot fewer of them that are done. PCI had not taken the 91 PCI had not. It was still on the upswing overall, and so there was like heart surgery was a big business. So they did want it, but if it's an uninsured patient, you're not going to make as much because you're uninsured than if you're a Medicare or a commercial insurance patient. All right, so the other thing that they did, which was kind of unusual but is worth bearing out, is we're talking a little bit about it. They instead of controlling for each of the comorbidities separately, they came up with a constructed severity index. And I'm pretty sure this was Dan's idea because it's the kind of thing Dan would be bothered about. What they did was they used basically a regression model where they regressed in-hospital mortality on a bunch of stuff, including the 30, all 30 Alex-Hauser comorbidities and a bunch of sociodemographic variables, including race. And then they used that prediction model, kind of like a risk model, to calculate each discharge's risk of mortality conditional on their specific set of comorbidities and covariates and stuff. But they only used data from the pre-period. From 88 or from 88 through 1991. Anyone have an idea why you might want to do that? So the alternative would be to like say, okay, let me put in all these things into the model together and just control for them outright. Power is not a problem. We've got hundreds of thousands of observations or something. Totally do it. Might make reporting a little bit different. So one argument might just be like it's a summary measure, so we don't it's kind of like the propensity score. We just load it in there as a summary measure rather than put in all the ones in this auxiliary set. Yeah.
Could it be an interaction effect that?
Say more.
So if you use data from during or post policy implementation, something there may exponentiate another variable that you use in the regression equation. So if you just focus on pre-mortality, there may not be that interaction effect.
I think you're close. I'm not sure if you use the words that I would, so let me say what I'm thinking, unless someone else wants to take a crack at it. Or
I just thought that their hypothesis was that patients post-report card area undergoing cabbage were potentially different with respect to those variables, and so if they want to construct an index for severity, I suppose it would be like an uncontaminated estimate to do it in a pre-period.
Is that because after the policy's in place, you might have the effect that you're only picking healthy patients that will?
Exactly. Yes. So the idea is, so if we just did it the way I proposed, which is just n plus bx, where x is all this stuff, right? We have pre and post in this regression. What are these coefficients captured? They're capturing the average effect of, say diabetes on receipt of getting a cabbage, averaged over the before and after period. But what if response to diabetes as part of the publication of the report card, what if surgeons' likelihood of treating CABG patients, or treating a patient with CABG, changed in the after period relative to the pre-period? We're not picking that up. We're just averaging over it. So we want, what exactly what Ted said, an uncontaminated estimate of risk. And the only way to get uncontaminated would be to say prior to the policy came along, because once the policy comes out, stuff might change, including reaction to an association between each of these coefficients, or each of these covariates, and the likelihood of getting surgery. So we want to control for all this stuff, but we want to do it in a way that makes sure that we're capturing your sort of, well, to use your word again, uncontaminated risk of getting of severity when, you know, that's uncontaminated by the promulgation of this particular policy, publication of the CABG report card. So that was a little side note. Okay, so what do they have in the model? Well, they have time, of course. They have pre versus post report card publication. Race, ethnicity, so minority versus white non-Hispanic patients, where they lump together race and ethnicity in the minority group. Although they did some stratified ones. And the state, so New York versus the 13 or so control states. And they put in two-way interactions and three-way interactions. So the model looks like this. Whether or not you got a CABG, they're using, we'll talk about in a second, as a function of the main effects. I don't include the other covariates in here. The main effects, the two-way interactions, and then the three-way interaction that captures the difference effect. That's the same ones again. How do we interpret this coefficient on the triple interaction? That's the differences. So now it's effectively how the black-white difference changed from pre to post in the New York versus the control states. Those are three different differences. We're looking at the unit of analysis is, well, we're using a difference in difference, but instead of levels, we're looking at the black-white or the white minority difference is itself the unit. So that is the key thing. We difference in differences. Three differences. So how does this look visually? So here we have on the left 2 by 2. We have the control states. On the right we have 2 by 2. We have the New York state. And basically all we're doing is we're saying, well, when we had a standard diff and diff here, we're comparing race equals 1 to race equals 0 from pre to post in New York. So we can calculate delta New York minus gamma New York, and the difference in that from the difference in beta New York versus alpha New York, and compare that to the comparable difference in differences. Subtract here, this is difference in differences New York, this is difference in differences control state, and we get, again, the difference in difference in differences, thus leading to difference in differences in differences. What happens when we add control variables? Well, you know, we're hedging because of a repeated cross-section here, so we're hedging against omitted variables bias, because there may be things that differ across patients in the different states over time. So we want to control for those as much as we can. It makes the estimation a little more efficient, but it doesn't materially affect our triple difference interpretation, right? It's still the black-white difference, how the black-white difference changes from pre to post in the treatment versus the control states. But now it's conditional on whatever else is in our regression model. We're controlling for all that stuff, so the actual estimate might change, but the structure of the triple differences doesn't change at all. And how do we estimate said model? Well, because Rachel and Dan are health economists and David doesn't really care, they use a linear probability model, even though this went to a clinical journal, and it's a fairly, it's 2005, so it's almost 8 years ago. I think this is a potential, it's a good example, at least, of using a linear probability model in a clinical journal. They used linear probability model and they had to go through a number of checks. In particular, they checked the proportion of predicted probabilities that were outside the unit range. So it doesn't mean anything to have a probability above 1 or below 0. So they found only 4% of their predicted probabilities, that's 4% of discharges in their entire model, and this was a set of a couple 100,000, fall outside the range. So that's reassuring, even though it's kind of irrelevant, because we're not actually interested in the predicted probability, right? We're interested in the coefficient on the differences. Yet, nevertheless, this is window dressing to say, at least here, to say Oh, it's okay, don't worry about it, it's not terrible. And then, because of the intrinsic homoscedasticity built into the linear probability model, they both used the robust standard error option, but then they also did another econometric thing called estimated model called weighted least squares, which is another an alternative to the robust standard errors when you know the form of the heteroscedasticity, blah, blah, blah. Basically said, look, we did it this way, we did it that way, we have a lot of sites, it's good to go, trust us, okay, it's all good. It's not, you don't like it, but we're using this linear probability model for a good reason, which is what? Why use the linear probability model? Why not use logistic regression? Because our dependent variable is binary, right? And binary variables should be modeled with logistic regression. Everyone knows that. Only a real idiot would use a linear probability model.
Could you determine more of the difference if you make it continuous?
Like what continuous?
Isn't it likelihood of getting cabbage?
Well, yeah, but the dependent variable for each person is still, did you get it or did you not? So it's still a binary. I mean, instead of modeling the loads of the probability, they're modeling the probability outright.
Easier to interpret rather than odds ratios.
Totally, right? So it's already on the probability scale. Those coefficients are immediately interpretable as percentage point differences in the effect. That triple difference coefficient, bang, immediately interpretable. Not having to deal with ratios of odds ratios. Don't know how to interpret that. Does not compute. Okay. So, same grid again, but now with actual numbers in it, taken from the paper. Again, New York control, we see, here's the whites, I use B for blacks, I can't remember if this is actually the black numbers or if this is the composite group. In any event, well, we can see what? Even in the control, so forget the report card business over here, there's no report cards. Cabbage use is going up among both. So we've got this, we've got this context that if we just look at the post period, we might be omitting the fact that there's a secular trend of increase in cabbage. It's also going up here as well. So didn't we say that it should be impinging on minorities' access to cabbage? Well, so shouldn't this be a decrease? Well, no, we're saying it's a relative decrease. So the counterfactual is not did it actually go down, but did it go down relative to what it would have if there weren't a report card? So you could say, all right, well, we could compare, here's one set of counterfactuals, non-minorities in the same state. That seems like a reasonable one. Here's another set of counterfactuals, minority basis in other states. Why don't we just put them all together and we have, again, difference and differences and differences. We have both. We're comparing the black-white difference in the treatment state from pre to post to the black-white difference in the control states from pre to post. Hopefully by now I've said it enough times that hopefully it makes sense. I don't think it's conceptually just more differences, right? Here's a nice graph that I think going back to Rick's question, I think Lisa, you asked the question, right? Maybe it was about how do we understand the differences. Here's a plot of the time trends in the state race difference and differences. So with confidence intervals, another way to look at this number, we're actually the unit here is not a single difference. Each one of these points represents a difference in differences. It is the relative difference of the black-white difference in New York minus the black-white difference in the control states. And so if it's higher, then we're the way they structured the particular graph, if it's higher, blacks in New York are worse off relative to whites in New York compared with the black-white difference, the concomitant black-white difference in the control state. Positive values are bad. What we see here is we go from kind of like, here we go, we're trucking along, things are getting better, and then we're actually favoring minorities, and then boom, the publication comes out, and then it kind of like attenuates over time.
So does that mean before the policy that like New York was actually better than other states?
In fact, minorities in New York were disproportionately more likely to get,
because it's less than, so zero would be the same.
Zero would be everyone gets it the same, right?
So this tells you that there are racial differences in New York that change at a certain point in time, but don't tell you, they don't allow the comparator of the other state that didn't have the policy.
No, they do. This is all built into the single point. This single point is a difference in differences. This is the black minus white difference in New York minus the black-white difference in the control states.
So how come it's not a triple D?
It is a triple D because we have time right here. So if you take these, kind of the weighted average of these, and subtract them from the weighted average of these, that's the third arm, the third difference.
Okay.
But there's just a different. This is the year by all the numbers that they presented up front were just single period, kind of like post versus pre, all combined together. Here we want to unpack it a little bit and say, how does this thing proceed year by year? TikTok, this is arguably what you would expect if the policy were having the kind of effect we think it would, like sharp response, attenuation over time. By 2000, it's all gone.
Can you go back to the actual numbers, because it just...
Well, those aren't the actual numbers, but, I mean, yeah.
Oh, these aren't?
No, I mean, these are the numbers, but the graph I just copied and pasted, as opposed to manually entering by hand these numbers from the manuscript. These are from somewhere in the manuscript. I didn't make them up. I don't think I did.
These are rates at which they're getting cabbage, or?
Yes. So up by 2.1%, but up by 4.4%. Up by 2.9%, up by
So what's the
2.7%.
denomination, 3.6%
Of AMI patients
MI patients, sorry.
admitted to the hospital.
And it's average before and after the intervention. So like all of these points after 1991 are averaged for what's time equals 1.
Time equals 1 is the post period, which I think in the main analysis is through 95 or something like that.
Okay.
And pre-period is 4 years, but I'm sorry, Dave, you were still asking.
Well, I'm confused because it looks like in time period 0, in New York, there's like a really low rate of black patients getting care. But I thought the next graph says that they're more likely to get care.
So it's the relative difference, and so it's the difference in differences. So here they are relative to the white group, they're 3.4 percentage points off. Here they're only 2.5 percentage points off. So blacks are, in an absolute sense, better off relative to the whites in New York than they are relative to the whites in the control states, even though they have a lower actual rate, because we're comparing them, in that graph, we're comparing them to the difference in, we're comparing differences, not levels.
Right, but then the thing is, when you think about it in absolute differences, it's a little bit, doesn't it feel weird? Because it looks like, if I just looked at this, I would say, oh look, like, black patients in New York in time 0 are 1/3 as likely to get cabbage before, and then look afterwards, like the race, like by race, their likelihood triples.
Right. So I mean, you're saying, well, an alternative way to look at these data is on a proportional basis.
Yeah.
And you might get different, you
Yeah.
might get a different interpretation.
Yeah, you get a totally different interpretation, no?
I didn't write the paper. I mean, like, I understand what you're saying, and I'm not disagreeing with you.
Because, I'm just looking at that data, and it tells me one story is that basically in New York, from time 0 to time 1, the absolute rate of cabbages in black patients tripled, right? Comparatively to whites, which only doubled.
Right.
So I feel like, if anything, maybe that's...
Well, so I would say in response, like, and one thing you're not controlling, like, with small numbers, you get very quickly, you can get different rates of, a proportional change is, okay, yeah, but they have different baseline rates. So saying these guys doubled and these guys tripled may not be a good interpretation because they're not at the same baseline, and because with a higher baseline, it's harder to mathematically you have to have bigger numbers to get us the same proportional. You have a bigger absolute increase to have the same proportional response, right? So should this be an absolute difference or a proportional difference? That's an analyst's decision. Someone could look at these data and say what you're saying and say, still at the end of the day, like, they're worse off. What they used was an additive model and looked at absolute differences and said, okay, on an absolute difference, this difference shrank from pre to post relative to the comparable pre to post change in the black-white difference in those states.
So is it two different questions? So going to what he's saying, so if you're saying that, am I better off, if the question is, are you better off as a black person to get a cabbage, then maybe it's good. But if you say, are you better off disparities wise, then you wouldn't want to be in New York because they had more disparities, even though they had higher rates of cabbage in minorities.
I mean,
No.
you know, so looking at it and saying, where's it better, like, where are you better off? If you're a minority patient, where are you better off? It's say something about the basic, the actual rates of use, not the differences.
Right.
And really it's going to come back to what's your counterfactual? What are you comparing it to? So there may be reasons why minority rates are different that aren't explained in the model. I mean, that get differenced out in a triple differences setup, but are like, that's the kind of the omitted variables bias challenge is more pertinent in the case we're looking at levels because you're not sure. Why is it that blacks versus, like, the black rate here is 0.9% and here's 2.5%? Are they significantly different? Yeah, maybe. They are because we have a lot of data. I don't know. But, you know, New York, MI patients in New York may be somehow different from MI patients in the control states. We don't know. If those factors stay constant over time, a difference in differences model will take care of that. We don't know, but whatever it is, we're comparing New York to itself, pre to post, and to non-minority patients in the same state during the same change period. So I mean, I'm not going to tell you exactly these are like the paper that's peer reviewed. Peer review doesn't mean a whole lot, but you know, it's kind of like this is the way they accepted the data. This is the interpretation conditional on how you analyze the data. If you analyze it a different way, you can wind up with different conclusions. Welcome to research. And I mean, it's part of the game. You say the slope goes down, I say it goes up less. Anyway, they found a nice fat significant result here. So I don't want to spend too much more time on this, but are there any questions about triple differences? And you know, hopefully, like, I don't know if you actually read the paper, but you see the setup pretty quickly and you start sniffing, it smells like triple differences, right? You got a state policy that affect, and you want to look at some sort of racial difference or some kind of difference within the population. Like, how does the policy differentially affect A versus B within the state? Policy comes out at a specific time, so you got the pre-post right there. It's a single state, so you're talking about the treatment versus control. And then as soon as you start looking at minority, non-minority differences, or just like affected this part of the population different from that part of the population, triple differences right there. I mean, it's just got triple differences written all over, and they took it and they got it into circulation, which, I mean, it was a great outcome. It's a good paper and a great outcome. Whether or not you agree with the results of the interpretation, that's totally cool, like, but they still got it in circulation. So.
Can I ask one question?
No.
I got
Okay.
lost in terms of where PCI comparator came in.
Oh, I didn't present it. Was it in the paper?
Well, I guess I'm thinking about it in terms of a control versus the fact that in the triple D we're using a state as a control.
Right. So they ran a whole nother set of control, a whole nother analysis. Well, let me look at this one. A whole nother analysis looking at same stay CAS rates and same stay PCI rates for MI patients, right? So and I think, from what I recall, this is what they found, that there shouldn't be a significant difference in PCI, in the triple difference in PCI or CAS rates, because the presumption was the policy wasn't differentially affecting minorities for PCI or CAS, because there's no mechanism, at least that we came up with. That
It's
would
like
affect
what
it.
you said the other week about your placebo.
It was last week. Yeah.
Last week. Okay, I get it.
Yeah. So I mean, you could, in theory, have said, okay, let me use PCI patients as a fourth difference.
Mm-hmm.
But you know, at some point, it becomes a little hard to interpret, and it may. I think rhetorically, it worked for them better to use PCI as a separate outcome and CAS as a separate outcome, and say, here's a placebo test, but stick with the triple differences, which is already a lot of differences. I don't know that I've ever seen a quadruple differences. So you can do a quadruple bypass, so I can't do a quadruple differences. You know, just because you can do it doesn't mean you should. You got hard to interpret.
Can you reiterate what you said about logistic versus linear? And can you just say, was anything lost by doing linear instead of logistic?
Statistically or rhetorically?
Rhetorically.
So, what they wanted to be able to say was, in this triple difference model, let me add up these differences.
Mm-hmm.
Linear model is set up for that. It's already linear, it's additive, so it's boom, it's straight away, you get the coefficient on this triple interaction term from a linear probability model, right there, and it's immediately interpretable. If you go to a logistic regression, now you're not modeling the probability that y equals 1 anymore, you're modeling the logit of the probability that y equals 1. So then the predicted probability becomes a function of all this stuff plus all your other covariates. So then you have to compute average marginal effects or something, or you report the odds ratio on this triple interaction term, the direction of which might mean something. And so you could say, is this odds ratio significant? Which I think is trying to channel the epi biostats response would be, okay, we have the odds ratio here, let's just report that. If it's positive, then it's positive significant, then that would be, negative and significant, that's what we would expect. That minority patients are relatively worse off than white patients in the same state from pre to post treatment versus control. And you can say that, okay, we got the odds ratio, here's what it is, it's significant, our results are significant. When we write it up, as long as we're careful about saying the odds of getting a cabbage or disproportionate blah, 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 I think it'll be fine. But it's like, well, what is that? Like, it doesn't give you a sense of the real magnitude of the effect, is the argument the economists would make, or the linear probability model aficionados. They said, okay, we'll use the LPM, and LPM is particularly good in a case where you've got a lot of power, you've got a lot of, like say you're studying the effects of duty hour reform, for example, right? And you've got a lot of observations, same kind of thing, and you've got a policy. People have used logistic regression, and if you're already set up to do that, that's fine. But if you're reporting odds ratios, and then it gets in a jam, well, great. You know, what's the argument? But you may have a hard time understanding, like, what the magnitude of the effect really is, except it's significant from 0, in the right direction.
Thank you.
Sure.
I'll stop.
No, you can ask questions, as much as you want. But I have to stop talking in 35. Oh, less time. Okay, so I'm rapidly falling behind again. But I know you love it. So I've been wanting to show you these margins examples for a long time, and we keep running out of time. And I said today I'm going to do it no matter what, and yet I think it's probably best for me to skip over them because I need to keep on track because I'm running out of time with spring break, which is not movable. So I'm going to skip over the margins examples and see. It's not really cool though. It's really easy to say, okay, look at that pretty picture. I did that with one line of code. I did that with one line of code. That's the Florida versus New York difference in drug-eluting stent use over time in levels. Pretty damn easy, right? And then at the end, I computed the Florida versus New York difference over time and plotted it all with one line of code. And then there was a couple lines of code to figure the difference and then apply it. But anyway, the point is that Stata can do some really cool stuff with margins plot. I do want to show you this though. Okay, so this is with respect to interactions, right? So I just want to go over, in Stata, this is how we would expect, one way to specify a two-way interaction. We have a regression model, our outcome variable is length of stay. We have an indicator for whether or not you got a drug-eluting stent, and an indicator, a set of indicators for whether or not what quintile of propensity score you were in. This is how old this example is. Remember back to propensity scores, we put everything into quintiles of propensity scores, category of 1 to 5, whatever it is, right? And then the first variable, single pound sign, second variable gives us the interaction term. We could have done the same thing with just this double pound that. The double pound, 2 pounds, says I want the main effects and the interaction term. The single pound says I just want the interaction term because I put in the main effects myself. What do you get from Stata? You get an estimate of the main effect, for DES, an estimate of the main effect for the quintiles, and then their interaction terms. Note that we don't have a main effect for when quintile equals 1 because we can't put all 5 categories in. 1 falls out because of the omitted referent. And so we get 4 estimates there and then 4 interaction terms. Any questions about that?
I mean, just in general, why would you do double count versus just putting it in?
You know, because having.
But it's gonna give you the same
It's
thing.
giving me exactly the same
It'll
thing.
give you the same output.
It gives me exactly the same output. It's like, do you use 2 slashes or slash star slash blah blah? Have it, I think. But let me show you something else. This is a different way to specify the same model. Here is the original specification, main effect, single pound interaction term. But what if I just put in main effect for the quintile and then the interaction term? So I leave out the main effect for DES. I still want it in the model, but I want to understand what it is. I want to actually, the purpose of doing this for this particular example is to say I want to know within each quintile, what's the difference in length of stay by whether or not you've got a drug-eluting stent versus not. Okay? So quintile 1, what's the difference? Quintile 2, what's the difference? Quintile 3, what's the difference? I can get that same thing from this model, from the original model, but remember, this is the main effect of drug-eluting stents, this is the main effect of the quintile, and then each of these interaction terms represents a difference in that thing. So this is the average effect of getting a DES for the first quintile. This plus that is the average effect of getting that difference for the second quintile. This coefficient right here tells me for the second quintile how much different is the effect of getting a DES on length of stay, from how much different is it for the second quintile versus the first quintile, right? So what I want to do is I want to add this to each of these things. I could do it manually using test or lincom or whatever, right? But I could, by doing that other model specification, I can say, look, here we go. I want to get the main effects we don't care about, and then for each of the 5 quintiles, I want to know what the average difference is in length of stay between whether or not you got a drug-eluting stent or not. And it tells me right here. Notice that, you probably can't see it because it's so damn small, but 0.321, right? That's the same coefficient as the main effect on DES, which is what I told you is the main effect when the quintile equals 1. That is the difference in length of stay when you're in the first quintile of risk. So, bang, and this number right here, 0.608, is the main effect plus the difference. It's all just rolled up for me right there, so I can tell without having to do the manual combination myself. Sometimes that's really useful in work, especially when you're looking at time trend data. You want to look at over time, each year, how big is the effect? Specifying the model in that way will give that answer to you right off the coefficients. How big is the effect right there, bang, 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 in each year. Can be useful. Trust me. Or ignore it. All right. Finally, penalty. So, we talked about difference of differences, and difference of differences is actually a pretty nice segue into panel data. So, for a while we were talking about cross-sectional data and trying to get a causality by covariate control or matching or propensity score stuff, right? That's one way to get to causality. Longitudinal data or panel data gives us another opportunity to get at this, taking kind of some of the principles we learned in difference of differences and going a little bit further with them. So let's first the setup. Suppose, this is panel data, suppose we have multiple observations in each time period, across time periods for the same unit. So we follow individual states, whatever, hospitals, bang, 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 each year of our study. We then can specify a conceptual model where our outcome, now indexed by I and T, I for individuals, units, T for time, is a function of an intercept, a treatment effect, which can vary over time. Say you're 0 in the pre-period and 1 whenever the post you actually get the treatment. It can also change, so you could flip on and off. It could be a continuous variable, so it would go up and down, whatever the treatment is. And then 2 sets of covariates. One set of covariates is time varying, so things about you that might change over time. Another set of things, Z sub I, by assumption, are the things about you that are not time varying, that are time invariant. Simple model now, we're making it more specific by adding time to it. We can expand it a little bit, but only, this is a kind of, not even a trick. We can say, all right, let's take that error term, E, and decompose it into 2 pieces. U, which is time varying, idiosyncratic, and V sub I, which again, by assumption, is time invariant. the key thing about the panel data models, the panel data approaches, are that we're going to, again, you've already seen first differences, I'll show it to you again in a second, we're going to be able to get rid of all these things, both the observable things about you that don't vary over time, but also all the unobservable things that don't vary about you, that don't change about you over time, without actually knowing what they are. So here's the example of first differencing, and first differencing is a particular approach, but it's an example of the general approach. Suppose we have data on you in 2 periods. It's the same unit of analysis. So we index you yit equals 2, yit equals 1. Here's your model in the first period. You've got your treatment status, your time variant covariance, your time invariant covariance, and then your error term in 2 pieces. Same thing in year 1, except it's not everything's indexed by 1. Subtract the 2 at the first difference part, and lo and behold, you're now modeling the difference in the outcome as a function of difference in treatment status, difference in time varying stuff, and the difference in the error term that also varies over time. As promised, Z and V, the things about you that are either observable or unobservable, simply fall out of the model, simply by subtraction. That is what we get. That's the fundamental insight into getting longitudinal panel data and going with fixed effects type models. We are letting each unit, serve as its own control in some sort of analysis. And by doing so, things that don't change can't influence the outcome, because by construction, they don't change. So how do we, formalize this just a little bit? Apply the conditional independence assumption. In cross-sectional data, we said treatment status and baseline outcomes are assumed to be independent, conditional on the observables, right? So just our expected value or the outcome conditional on X given treatment equals 1, given treatment equals 0 is simply the difference in the expected outcomes, conditional on the X's. In panel data, now we're just simply changing that to, instead of, this should actually be changes in baseline outcomes, are independent conditional observed covariance. So now I just added a delta to represent the change, the simple arithmetic difference of the two. And we're saying, where we had levels before, we're now looking at changes. So all the things that don't change over time, by construction, shouldn't be affecting the change in your outcome. I want to harp a little bit on this panel versus pooled cross-sectional data issue again. So I just said to calculate first differences, we need observations on each year of the unit, each year that each unit is in the panel. And then so it bears questioning, if we have pooled cross-sectional data, what are we actually controlling for? Let's take an example. So this is kind of like the Werner, Ash, and Polsky example. Suppose we have a state level policy, and we want to study its effects on outcomes. And we have data on a different sample of, say, hospitals for each year, each state and each year. Instead of if we had the same hospitals, we'd have a panel of that data set, right? So how can we analyze these data? Well, we can treat them as a pool of cross-sectional data and estimate differences. So our estimating equation then is, let's model outcome for a given state at a given hospital in a given time period as a function of a state indicator, a time indicator, their interaction, that's the difference in differences, and then time varying or covariates that vary by state, hospital, and time. We get rid of the state level time invariant things because those are perfectly correlated with the state indicators, and we're left with an idiosyncratic error term, right? So this is the key point. Anything that is time invariant, that's constant over time, is captured within a given state, at the state level, is captured by this indicator. That's what we're controlling for by putting the state indicator in there. So we don't need anything that we can't put anything in. If you try to model, put in the same model specification a state indicator and something else about the state, that state population, well, state population changes. Square area, borders don't change, right? So square area, square miles of a state area, right? It's constant over time. it's perfectly correlated with the state fixed effect. Anything that's constant over time in this model is going to be perfectly correlated. They can't both be in the model, so one of them will fall out. But the important point is that even though we're controlling for state level factors, we're not necessarily controlling for hospital level factors that might vary over time. So we can control for them the observables by adding them to the model, but we can't be sure that the hospitals in a given state are the same pre to post, right? By construction or by assumption, here in the beginning we said we had a different sample of hospitals. Maybe they're randomly selected so that they should be equal to each other in expectation. But that would still assume that the population of hospitals in a given state didn't change over time, potentially concomitant with the policy introduction. If we had the same state hospitals, or the same hospitals in the given sample, we could be confident that by controlling, letting them serve as controls for themselves, they would be holding constant anything about those hospitals that didn't change. In this example, we're assuming that the unobservables among the different hospitals are going to be unaffected. To get a causality, we would say, by assumption, to get a causality, we need to assume that the hospital level factors, unobservable hospital level factors, are not changing. You can say the same thing I just did about hospitals and apply that to patients as well. Is the population of patients that you're studying in this given example also changing over time? We can control for observables like Werner, Rachel and company did in their model, right? By controlling for using their severity index, controlled for a whole bucket of stuff. And then that would capture differences in the patient level issues over time. But it doesn't control at all for unobservables by construction. Only by having the panel data at the unit that you want are you actually able to control for unobservables at that level of analysis. If you have a panel data of hospitals, you can control for hospital time invariant things. But if you, just because you have states, if you have a different sample of hospitals over time, and you don't have panel data, you still have a powerful design, but it's not as strong. It's important to understand why there are differences. So pooled cross-section has some great strengths. I mean, usually it's cheaper to collect, and it's you can usually get larger sample sizes out of it because you're not having to follow exactly the same in units over time. But be aware of the potential composition bias in your sample, that you can have unobservable differences from pre to post in your thing that you can control for with panel data that you can't control for with repeated pooled cross-section. And so just to go back to here, right, we can, in this context, we can control for observables at the I level, at the unit level here, by putting them in the model. We can't control for the unobservables. That's the difference between repeated cross-section and panel. An important point.
And you can't study, like you couldn't do the cabbage question in this because the patient, once the patient has cabbage, like you can't use them as their own control in the pre and post period. Because they're not going to get another cabbage.
Right, so I mean, so you can, and I'll show you, we have time, I'll get to like how to roll up a sample. You could roll that sample up to the hospital, right? You could say, we now have a hospital level analysis, or even a state level analysis, right? We can control for the observable characteristics, just like Werner et al. Did. But our panel is at the level of the hospital. That doesn't, so that accounts for things about the hospital that don't change over time. One of those things might be the composition of the sample of patients. But we have to assume that if we had patient level data, we'd be even better off, ideally. Although then you get into issues of what does it mean to be a multi-cabbage recipient? And like that in this context doesn't really make a lot of sense and probably would kill your generalizability. There are a lot of studies there's some number of studies in the world, and I think mostly psychology would have pervaded into economics as well, using twins. Twins are great, right? Because they have common genetic background and common environmental background for the most part. Sometimes you get little tricks like, let me try and separate the influence of nature versus nurture by looking at twins who were separated at birth and blah, 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 right? That's great. You can do all this great twin study stuff, but you have small samples. And what's the generalizability of twins to non-twins? It's kind of like studying stuff in the VA. It's like, it's great, we showed it in the VA, but the VA doesn't exist in the real world, so why should I publish this in my journal? Because you show up a particular subsection of people that are, like, VA hospitals are still hospitals, but they're different. Just like twins are special people, or they're people, but they're something about them that may be special, and therefore I journalize them. All right, I'm sure I got on that patch. No offense against me. So, I want to actually introduce a handful of model approaches. This is not that you can use to analyze panel data. So in the first bucket of models, we call change models, and there's two here, the change score and the first differences. I'll go into each of these in more detail. Third option is a lag dependent variable model, and the fourth model is called fixed effects. I'll try and get through these three today. We'll pick up fixed effects and whatever I don't get to today on Thursday. But this is the basic menu, I think, of ways to leverage panel data. I'll start simple. Well, none of these is that complicated once you understand what's going on. Well, you be the judge, not complicated. So, the first approach, which really is common, I think, more in the clinical literature than anywhere else, is the change score model. So here, the simple setup, and this is going to be true for everything I have to say today. The simple setup is we have panel data on 2 time periods. Some subjects received the treatment, DI equals 1, and some did not. And so we estimate a model. Where the slides will differ is in what they're estimating. So in the change score model, the dependent variable is literally the change score. It is you can normalize it, but it's the second period outcome minus the first period outcome. But what you're modeling on the right-hand side, what the covariates are the baseline measures, the first period measures of your covariates, and treatment status, and I guess the time invariant stuff as well, which doesn't vary over time. So in this particular setup, you have data on 2 years per 2 time units per observation, but you're only using 1 time unit per observation in the estimation because